Hi, I want to demo how we can do a flying shear system. This is going to be a simple example where we're synchronizing just one axis to a master axis, which is traveling at a preset speed. What you can see in front of you is a graph. It's a real-time trend, actually, of the flying shear system. I'm going to stop this trend and I'm going to go to a still graph to make it more clear as to what I'm trying to do here. What we have is a master where this is the master position and this is the master velocity, the black line, and this is all indicated by the legend here at the bottom left-hand corner. You can see that axis 2 is our master, and the black is the velocity, which we have going at 10 inches a second. And at this particular point where the cursor is at, the target position, or the master target position, is at 11.54 inches. And as I move my cursor back and forth, you can see how all the values change. Axis 0 is the slave axis, and what it needs to do is synchronize to the master axis and match speed, and in this case I have it so it matches the position, so it's matching not only position but or velocity, but it's also matching phase. Sometimes that's important. The master position is indicated by two lines here. There's a target and an actual position. If the system is tuned up correctly, you should only see the actual position because this red line here is on top of the target position. So start out at this point, and the master has just rolled over, so we're starting a new cycle. The slave then must ramp up and get in sync with the master position, and from here to here it's in sync. And in this case I have it so that the two must stay in sync for 0.4 of a second while some action is being taken. The shear is cutting, for instance. And then after that action is taken, the master keeps on going to the end of the cycle, but the slave must go all the way back to the start position and wait for a new cycle to begin. Other lines of interest here is the slave velocity. You can see the velocity goes up and gets itself in sync with the master velocity. Then it goes retracts, goes negative, and then gets back to the home position here. This is the slave acceleration, and I'm plotting these because it's necessary sometimes to know how fast the acceleration is so you don't exceed any limits. Now what I'm going to do is show the program. The reference program is pretty simple. Normally you don't need to have a reference program because it's being controlled by some outside line. For instance, say you're geared to a line encoder and you might not have any control over what the line is doing. But in this case I'm assuming that I have some control over it. So what this one step does, this one program, is it just saves away the old master velocity and it sets the cut length to the rewind position. So what happens is from an HMI you would set the cut length, and then the system will, the encoder counts or the position counts will automatically roll over at whatever the cut length is so you can begin a new cycle. I'm setting the master velocity here. I got a very slow accel and decel rate, and then what I'm waiting for is the master velocity to change or the cut length to change. As soon as the cut length changes, then we go back around and start a new cycle with the new cut length. Both the velocity and the cut length can be changed on the fly using this method. So this is the master program, not much to it. Slave program. I've got the comments out so you can see the 4 steps that's being executed here. The first step goes to the start position, and the start position is, I'm assuming I've got a travel length of 20 inches. the start position, I just set it arbitrarily at a ½ inch, but you want to make it as close as 0 as possible so you can get as much stroke out of your 20 inches or whatever actuator length you happen to have. I'm waiting for the in position bit here. Right now we don't have names for that, but I can always put in a comment. Wait for in position. And then the next step is where the program really begins, and we just kind of cycle through these 3 steps to do the normal part of the program. So the first thing we need to do is ramp up and get it in sync, and there are some calculations that need to be done ahead of time. So we have this expression block that allows us to do the expressions, and this is using structured text. What we want to do is gear up to a gear ratio of 1:1. That way the slave speed is matching the master speed. We're using the that's the master target position. That's our reference position. We calculate out a master sync position, a slave position. That's being calculated up here. Start position, the master is going in the positive direction, and the slave is always going back and forth, so we just say that it's going in the nearest direction. After it gets in sync, the slave axis, axis 0, has its move done bit set. It's not necessarily in position, this is a move done bit, and it means we're synchronized. And then I have 4/10 of a second, which I'm allotting to do whatever action, the shear. We could wait for a position to occur, an input to occur, or for some other axis to get out of the way. And then I need to do some calculations to calculate out a new master sync position, new master start position to go back. And what I want to do is set the ratio to 0 to 0. And that's the ratio of 0 gets us to the stopped location, which is stopped is down here. So going from a synchronized gear ratio 1:1 to the start position can all be done with one command here. So if we have a ratio of 0, then what ends up happening is the slave is not moving at all. Again, we're geared to the master axis. We've got the sync position, and this needs to be recalculated again because it's a different position from the position up here. Again, the start distance is different, but these parameters stay the same. We wait till the move is done and then go back up and then wait for the opportunity to ramp back up again, which is this phase right here. So step 1 is taking care of this. Step 2 is this part here. Step 3 is all the way back. Step 1 is here. Step 2 is this. Step 3 is all the way back. That's all there is to it. And then to see the data updating, we can go to the program monitor. Up here I can see the 2 programs running. One's the sync program, which is what we were just looking at, and the first program we saw was the master program here. And we can see the values changing. And if I need to change the master velocity or the cut length down here, I can change that by just changing these parameters and then changing it like that. Oh, by the way, we do have comments. I turned them off so that they would fit. These are the comments that we have for the program. And we can also put comments in line here. Oops. So we can comment our programs pretty well. And let's see, to set up the variable table, it's done here. This is where we set the initial values, whether or not we want to retain the values through power off. These are the registers that you would use to access our variables from the HMI or from the PLC. And if we are using a different brand of PLC, like an Omron PLC, we can change our address format. So we can choose Omron, or we can change Modbus, or we can change to IEC format. But we'll go back to Allen Bradley here. So let's go back to the program. This is because I changed the comments. To download the programs, I would just click on this, but I don't need to do that right now. I'm going to go back to the main program. This is our main display. This is being changed by changing the cut length. What we do is we're changing the position unwind. You can see the values changing here in the status bits. Here you can see the move done. Error bits, there shouldn't be any. And then to make this whole system run, we have a simulator. I'm going to go to all here. The simulator allows me to simulate a first or second order system. I can choose the gain, the time constant, the extend and retract limits, or the positive negative limits, and this way you can test at your desk. So let's go back to the graph and watch that again, and we can see that you can see that I changed the velocity up to 12 inches a second here. And this is what it would look like. This is real time. This is capturing the data every 10 milliseconds, but I can capture the data every half millisecond. It just looks a little bit extreme. Let's see, let me just type in half millisecond and then download that. Oops, don't want to do that. I want to download. And now here's my plot manager. Start the plot manager up again. That's what it looks like when we're capturing the data every half millisecond. So that concludes my demo.